Hi everyone, welcome to the second lecture. So today we're going to talk about hydrogel synthesis, applications, and characterization. With tissue engineering applications, most of the time what we're trying to do is mimic the native extracellular matrix. So in this picture we see a few different types of biological hydrogels in the form of hyaline cartilage, fibrocartilage, and elastic cartilage. And you can see how even with cartilage in itself, there are many different structures and organization and types of cartilage that are used. When we are trying to create a tissue engineering scaffold, we want to look at what tissue we're trying to mimic and then figure out the engineering specifications that we need to follow in order to help us make a functional hydrogel matrix that will serve the purpose of whatever we're trying to do. Some of the things you want to think of is the function. What's the actual function of the tissue? What are the mechanical properties? What are the cell types that are going to be there? Are there any signaling proteins that you need to mimic? Or maybe there are signaling proteins that can help regenerate tissue. It depends on what the application is, and that's what we'll go into throughout this lecture and in the discussion topic. Here are a few different mechanisms that we can release drug in the body, as well as the time-dependent curve of how the drug is released. So if we're just going off of pure diffusion, there's going to be a diffusion rate, and that will be a pretty linear curve, so a linear drug release over time. If you're going to rely on the biodegradation of the polymer or the hydrogel in order to release drug, then it's going to be less linear and more in patches. So there might be a steep initial curve and then it slopes off, and maybe over time chunks will come out, but it may be less controlled. In the case of swelling, you have a more logarithmic release, because typically swelling will occur immediately due to some sort of stimulus or just due to water infiltrating the hydrogel. And then when that swelling occurs, the drug will release and the scaffold will either degrade or remain intact, depending on what it's made out of. So this gives you an idea of which different mechanisms you can use to load drug into an implant or a scaffold or hydrogel, and how this can affect the drug release rate, which may also have an effect on how successful your scaffold is at doing whatever application you are set out to do. This figure gives a few ways that we can stimulate drug release using mechanical forces. So in A, you see a few different ways that we can measure the mechanics of materials. We can compress it, we can pull it and have it in tensile, or we can have it in shear forces. Some of the ways that researchers have mechanically induced drug release are using this shear force, compressive tensile forces, but now they're also shifting towards magnetic forces or ultrasound and things like that that can be more focused and targeted in the drug release. So getting into that, it brings up, how do we characterize the different types of hydrogels? If these hydrogels are releasing drug based on a mechanical stimulus, then their mechanical properties are going to dictate when or how strong that stimulus needs to be before you start to release drug. So how do we characterize this? Well, like we just mentioned, there's three different ways to characterize the mechanical properties of hydrogels. One includes tensile testing, another is compression, and another is shear. And actually this middle picture is of the rheometer we have in our lab, and it can do all of these three things. We have different attachments that allow it to measure tensile, compression, or shear. So depending on which test we're doing, if we're doing tension or compression, then we see over here on the right some equations. So we have strain equals the change in the length over the initial length. So basically how much it deforms. Stress equals the modulus times the strain. So stress is the response to a strain that occurred and can be measured as the force divided by the area of the face. So everything's relatively simple when you're talking about tension and compression. However, when you go into shear, these are simplified equations, but in general, the shear strain equals the change in position, change in x, the deformation, divided by the height, so the gap height between. And the stress can be broken down into these two components, G prime and G double prime. And G prime measures the elastic effects, or the sort of strength of the material, and G double prime measures the viscous effects, or the fluid-like properties of the material. So no matter which way that we measure, tensile, compression, or shear, we will get this stress-strain relationship where there are two distinct regions. We have an elastic region and a plastic region. The elastic region is where, however much you deform within the elastic region, you should be able to come back to its original point, so you don't permanently deform the structure of the network. However, once you pass this proportional limit where Hooke's law is in place, and you reach the yield stress, you start to enter the plastic deformation region. And this means once you enter this region, you've permanently deformed your material, and you can never get back to the original spot, the original properties of the material. So I want you to know each of these points on the graph. Know what is the elastic deformation region, what is the plastic deformation region. I'm going to give you a brief introduction to hydrogel rheology. On this image in the left, you see everything's covered by an environmental chamber to reduce evaporation. However, if we don't have the chamber on, it looks something like this in the middle. And if we go through the animation, you're going to see this red dot rotate back and forth. And while it's rotating back and forth, you're going to see this red and green dot move through this sinusoidal curve. So this sinusoidal curve represents the strain, so the deformation left and right in the red, and in the green the stress, or the response of the material. So as you rotate left and right, your strain is oscillating and you have a stress response. Now the delay in this stress response indicates how elastic or viscous your material is. So when the stress and strain are in phase, when there's no delay or lag between the strain being applied and the stress responding, then you can say you have a completely elastic solid, so like a rock or a piece of metal or something like that. If the stress and the strain are completely out of phase, so 90 degrees out of phase, then that means you have a viscous fluid, so like water. However, hydrogels are some mixture of the two, so they are considered viscoelastic materials. They are not governed completely by viscosity or by the shear modulus. They are more governed by the G prime and the G double prime that I mentioned before. And I'll go into some of the specific tests we do for rheology. So in the previous slide, each one of those oscillation measurements is one dot on this curve. So each measurement where we do the oscillation back and forth, we'll measure the stress, and then we'll come up with one data point of G prime and G double prime. So here we have a strain sweep measuring the G prime and the G double prime with respect to the shear strain percentage. So when we're analyzing a curve like this, we look at the region of linearity. So in the previous example, where we had the elastic region and the plastic deformation region, when we look at this curve, this side will be the linear viscoelastic region, and then this would be the plastic or the permanent deformation region. So this line marks the difference between, and that is represented by a constant G prime. But you see, once you get to larger strains, then the properties start to degrade. The G prime goes below the G double prime, which indicates that it's acting more like a fluid. And so all of these properties, the critical strain, the length of the linear viscoelastic region, the G prime, the G double prime, all of these are measurable properties that we look for when we do these types of testing. There's also something called the loss factor or tangent delta. So that delta is the time delay, the phase angle that I mentioned in the previous slide. So the tangent of that angle gives us the ratio of G double prime to G prime. So the ratio of this number to this number. The higher this number is, that means there's more viscous effect governing the mechanical properties of the material. So a high tangent delta means that it's more fluid-like, a low tangent delta means it's more elastic. Alright, so here we have another common test for rheology, where in this case we are measuring the G prime and the G double prime again, but with respect to the angular frequency. And in this particular material, we see this behavior response where we have the G prime below the G double prime at low frequencies. Then we reach a point where they intersect, which we're calling the critical frequency, and then the G prime exceeds the G double prime. So let's break down what each of these sections are indicating. So G prime is below the G double prime. That means it's behaving like a fluid. Then they meet, and G prime equals G double prime at a specific point. That's the critical frequency. So that's the transition. Then when G prime exceeds G double prime, it's behaving like a viscoelastic solid. Now this critical frequency, if you take the inverse of that, that correlates with the relaxation time of the material. And the relaxation time of the material is basically how the structure of the material is maintained over time during a dynamic experiment. So if you were to do like a creep experiment or a stress relaxation where you applied a force to the material, the relaxation time would essentially be how long it takes for that material to respond. So how long does it resist that change and maintain its stability? So the higher the relaxation time means the better performing or the stronger the material that is. So here we have another frequency sweep, but it looks completely different. What we see is G prime stays the same throughout all frequencies, so G prime is not frequency dependent. And what does this mean? Why do we not see this crossover? So what we're looking at is the difference between a physical hydrogel and a chemical hydrogel. So physical crosslinks versus chemical crosslinks. In the previous example, it's time dependent or transient dependent. It's frequency dependent. So that means that it's a physical crosslinker. It binds, it unbinds, and it goes through these different periods of binding and unbinding based on the affinity of the crosslinks to one another. So the stronger the affinity, the lower the critical frequency is, because there's a stronger attraction, so at lower frequencies they're able to form a polymer network. The weaker the affinity, the higher the critical frequency is. And conversely, or thus, when you calculate the relaxation time, the lower the critical frequency, the higher the relaxation time, the better performing the material is. Conversely, the higher the critical frequency, inverse, that's the lower relaxation time, and thus the material is performing worse. Now with a chemical cross-linked hydrogel, there is no time dependence because it's a permanent bond. So there's no binding and unbinding. It's just going to perform the same no matter what frequency you're testing at. Sometimes when you test really high frequencies, you can get some artifacts. But in general, frequency dependence is not seen in chemical cross-linked hydrogels. So you see this type of profile. So this brings us to the question, how are the application of chemical and physical hydrogels similar or different? So the transient nature, the binding and unbinding of physical hydrogels allows it to self-assemble and reassemble over time. So if that's important, that it's constantly, getting injured and then needs to repair or something like that, maybe articular cartilage could be an example of some place where you would need to have repair after multiple impacts or something like that. Whereas chemical hydrogels, once you break those permanent bonds, if you deform them past their elastic region, then they're done. They cannot reform their original structure. They will never perform like their original properties. However, from physical crosslinks, if you deform them past their elastic region, well, they can rearrange their network back to their original properties, pretty much, for the most part. So I have a little bit of a trick question, and that's, can a chemical hydrogel be injectable? I just said if you deform it past its elastic region, it won't go back to its original properties. So how could you inject this? You're shoving it through this tiny gauge needle, and you're injecting into the body. Of course you're going to deform it past the elastic region. So how could they be injectable? Well, the key to this is not forming the chemical bonds until it's already in the place that you want it to be. So you inject it as a polymer solution, and then whatever the stimulus is that forms the chemical crosslinks, whether it be like a two-part epoxy where you mix two things together and then they form a hardened gel. A good example of that would be fibrin gels, which one of you talked about in the previous section. Fibrin gels are basically like a blood clot where thrombin makes a cleavage of the fibrinogen molecule and then activates it to be able to polymerize and form a hydrogel. So that would be one example where you inject two solutions into the same spot and then they form a gel inside the body. Another would be if you had some sort of temperature-dependent crosslinker where it responds to heat or cold. You could have some sort of penetrating light. Near-infrared light is able to penetrate the body, so if you had a crosslinker that responds to the near-infrared wavelength, then maybe you would be able to inject that into a specific spot and then crosslink it once it's inside the body. So there are ways and different designs to get around some of these properties in order to make sure that they're strong but also able to get into the body without significant invasiveness. Here are some of the hydrogel properties and characterization techniques that you all talked about in the last discussion topic. And essentially what we're getting at here is how functional is your hydrogel for whatever application that you wanted to test it on. Your characterization techniques are completely dependent on the application, which gets into our next discussion topic. Here's a list of several different characterization techniques, but these are just a few of many techniques. So I encourage you to either investigate these techniques or look at your own or investigate specific properties of specific hydrogels. You could use the same hydrogels that you investigated in the previous section. You could look at other people's hydrogels that they posted about and see if there's another one that you get interested in. It's open-ended again, but just follow the prompt on the discussion format, which is going to be done on something called a Padlet. So I want to go over what this is first for those of you that have not used Padlet before. So I'm posting the link in the discussion assignment on D2L. When you click on that link, you'll be taken to this page. Hopefully. If you don't get taken to this page, then please send me an email and I will figure out what's going wrong. But once you get to this page, we have the prompt here. So essentially, each of these columns is a specific application. The other column, you can choose whatever application you want, just put that in the title, and then follow the same prompt. What I want you to do is write about a characterization technique that would be necessary for that particular application. You can describe the technique, you can describe what sample preparation is required, how the specimen is tested, what data is collected, how it's analyzed. It's really open-ended as far as what you talk about, but we really want to consolidate the information of what characterization techniques are required for each type of application. And of course, the same characterization technique can apply to multiple applications. I know that some of you might end up doing this later, some of you will be doing this earlier since this is an asynchronous format. So I put some different options for how you can respond and what you can put in your post. If you're coming later and you think, oh, all of the good choices are taken, then just do one of the other prompts such as instead choose a hydrogel that you believe would be useful for one of the applications and indicate what the measurement of that property is for that material. For example, if you're saying that, oh, this hydrogel will be good for tissue engineering of a specific type of cell, and the shear elastic modulus is 2 kilopascals, which is exactly the mechanical properties that that cell likes to seed onto. So it will attach to this implant, it will like this implant, and it will mimic the extracellular matrix that this cell is typically found in. So go ahead and move on to the discussion. If you have any questions, again, please contact me by email. Like I said in the announcement, I will be posting my next section on April 9th, and that will be focused on tying everything together into how to design from the ground up using all the information that we've talked about in the first 2 sections. That will essentially be the review for my exam question. So I hope you all are staying safe and healthy, and good luck with the assignment. And again, let me know if you have any questions or need any help.